Hello everyone, I hope you're doing well. In this video, we'll see how to draw planes from given Miller indices in hexagonal unit cells. So we have a variety of planes in here and we'll be drawing all of them in this video to see and learn the method to draw planes from given Miller indices. Okay, we can see here that we have these four examples where there are four indices, and we have also those examples where we have three indices. So you must know that there are two types of index system in here. The first is Miller indices and the second is Miller-Bravais indices. Miller indices are actually three in number. For example, as we can see, this is first index, second index, and third index. So there are a total of three indices and they are called as simply Miller indices. Okay, and we see them frequently to be used to represent planes and directions in cubic unit cell, and they're also used in HCP, but not exactly or frequently, because in HCP we use four index system, which is actually Miller-Bravais indices, where we have four indices to represent the planes and directions in HCP. Okay, in HCP actually there are further things that we need to know about the unit cell than these three indices can tell. So that is why we use Miller-Bravais indices more frequently for HCP. But if we know the Miller indices for the plane, we can convert them into Miller-Bravais indices as well. We'll see that how we'll draw these two in HCP. Okay, because sometimes students are given with Miller indices and they are told to draw them in HCP. So we'll have all kinds of problems in this video. So let's quickly get started. One more important thing to notice here is that we have these circular brackets here. Whenever the indices are given in circular brackets, it means they are for planes. Whenever the indices are given in square brackets like that, okay, when they are given in square brackets, they are the indices for directions. You should know the difference, because sometimes they don't mention whether they want you to draw planes or directions. So you have to make a guess from the representation they are using. Okay, if it's circular, you are drawing the plane. If it's square, then you are drawing the directions. Let's quickly get started. This is the first plane in line, and we can see there are the four indices, and I'm going to call the first index as H, second index as K, third index as I, and the fourth index as L. These are just the names that I'm giving to them, okay, so that I can call them. You can use your own, like U, V, T, W is sometimes used in other books, but I'm using H, K, I, and L because I have used the same notation in all of my videos. That is why I'm continuing on that. If you prefer this notation, you can continue it because the method is same, and this is just the name, and name doesn't matter. We should know the method. So this is the H index. I'm calling it as H index. K, I, and L, these are actually indices. And since we want to draw this plane inside a unit cell, which is HCP, so we should form a link between these Miller indices and the coordinate system that we are going to use in HCP. Okay, so the first index relates to the A1 axis, the second index relates to the A2 axis, the third index relates to A3 axis, and the last index, which is L index, that relates to the Z axis. Okay, and let me tell you that in HCP we use a different coordinate system than the one that we use in daily problems. Like, we are familiar with x-axis, y-axis, and z-axis, but in HCP specifically, we use these coordinate axis lines. Okay, the first is A1 axis, the second is A2 axis, the third is A3 axis, and the fourth is the z-axis. Z-axis is actually the same as the one in Cartesian. We'll see that shape. It's not difficult, it's just that a little bit different because the names are different. Okay, you'll see it. It's a really easy method. I'll show you it in such an easy way that you can do it in a fingertips. So that's really easy. The H index will be related to A1 axis, K is related to A2, I will be related to A3, and L will be related to Z. All right, and you should keep that in mind, that the planar indices, the indices of plane, gives us information. Indices of plane that we are given, they gives information about the intercepts of planes. Okay, they actually help us to know what are the intercepts that plane makes with these four axis lines, and those intercepts are used to actually draw the plane inside a hexagonal unit cell. So intercepts are the actually points where the plane touches the axis lines. Okay, I'll make it clear while drawing it. So H index will give us the A1 intercept, K index will give us the A2 intercept, I index will give us the A3 intercept, L index will give us the Z intercept. Let's continue the process. Just imagine that you are just given with the problem, and I'll do it in a better presentation so that you can replicate it on paper. Here I'm gonna draw a table H, K, I, and L. Okay, so this is kind of table. We'll perform the operations here to get the intercepts from these Miller indices, and that process is actually only one process. So these are indices for planes. Let's write these indices. H index is 0, K index is 1, I index is -1, and L index is 0. Next, we'll take reciprocal. Taking reciprocal, we'll take reciprocal of each of these indices. It's 1 divided by, reciprocal means dividing by 1. So we'll divide all of these indices by 1. So it's 1 divided by 0, 1 divided by K, which is 1, 1 divided by -1, and 1 divided by 0, which is 0. So what result we get after taking the reciprocal? 1 over 0 is infinity, 1 over 1 is 1, 1 over -1 is -1, 1 over 0 is infinity. So these are actually, after taking reciprocal of indices, we get intercepts. This is A1 intercept, this is A2 intercept, this is A3 intercept, and this is Z intercept. You can write it down here. A1 intercept, this is A2 intercept, this is A3 intercept, and this is Z intercept. That was the all calculation that we needed to perform in every case that we are having for the 4-index system. You have to find out the reciprocal and you will get the intercepts. Now the next step is to draw them inside a unit cell. And for that purpose, we first need to draw the unit cell, and then we should understand what is A1 axis, A2 axis, A3 axis, and Z axis. And then we will understand what intercept means while drawing them. Let's draw it. You should know a hack while drawing the HCP unit cell, because it's a bit tricky. So we'll draw first line like that. Okay, and then you will draw another line like that. Okay, it will be but approximately the same length as this one. Okay, but little bit, you can see that this is forward and this is backward. Then we will join them together like that. Okay, this is the roof plane. Now we have to draw the similar diagram right below. This corner should come just right below here. So these lines, these straight lines, should start from the similar point that we did here. So it's like that, and we'll start this one line as well from the similar point and end it at the similar point. Okay, and do it like that. You can see it. We draw the same, this hexagonal thing here and here as well. Okay, and I told you how you can do that. You'll draw the straight lines which are of equal length. One is forward and the other starts a little bit backward. Okay, backward from the point it was started. So you can see what I did. Then join them together and draw the exact similar one just below it. Okay, so you can do it by extending the lines so that you can know where to start this straight line, okay, where to end this straight line, and you will get it. Now we'll join the corners together this is how you are going to do that. They are actually the equivalent points. You can see this point is equivalent to this point. It's right below it. Okay, this point, which is upper point, is equivalent to this upper point. This lower point is equivalent to this lower point. This upper point is equivalent to this upper point. This point is equivalent to this point, and this point is equivalent to this point. So we'll join all these equivalent points with each other to get the hexagonal structure. So this is equivalent point. We'll join with this one with straight line. We'll do the same here. Okay, this point is equivalent to this point, so we'll join them together like that. This point is equivalent to this point, we'll join them together. You can see how seamlessly we are drawing this HCP unit cell. This point is equivalent to this lower point, lower point, lower point. Okay, equivalent points are joined together, and we have got the HCP unit cell. Now we need to draw the coordinate system, because coordinate system guides us to points. Okay, coordinate system helps us to define what does 1 mean, what does 0 means, what does infinity means. Okay, so coordinate system is scaling, and we have to do that scaling. This is the center point, and that point is origin. Okay, unlike the xyz axis, it's different. So this is the origin. Directly above it is the z-axis. Just like in the normal one, this vertical line is positive z-axis, and below it will be the negative z-axis. We don't need that because all of the indices that we have in here have positive z-axis. So we'll have that case as well where I'm gonna take negative z-axis for you people to know that how to deal with that case when it arises. So this is positive z-axis. Next we need to draw the a1, a2 and a3 axis. So for that purpose, what we need to do, this is origin and this is one of the corner on the unit cell. So starting from origin, you will draw this line. This is positive a1 axis. Then leave this corner. This is the corner that you took for a1. Leave this corner, the next corner in line. Draw a line from origin to this point. This is the positive a2 axis. Then moving ahead, this point, leave this point. The next point in line will give you the positive a3 axis. And that's it. This is positive a1 axis, leave this point. Next point, a2 axis, leave this point. Next point will be a3 axis. As we have defined the positive directions, we need to define the negative directions as well, because we have negative indices as well. So if this direction, this is origin, this direction is positive a1 direction, so the direction directly opposite to it is negative a2 direction. This direction is negative a1 direction, sorry. This direction is positive a1, this direction is negative a1. And similarly, we can see this direction is positive a2, and the direction just opposite to its opposite to this corner is this corner. This direction will be negative a2 direction. We can see this is positive a3 direction. The corner which is directly opposite to is this. So this will be the negative a3 direction. Alright, so we can see that we have all these positive and negative directions all at one place in a single unit cell. And the only issue is with the z-axis, and we'll see that how to deal with negative indices for the z direction. So now let's draw the plane, the first plane that we had, and we can see we have a1 intercept as infinity, a2 is 1, a3 is -1, and z intercept is infinity. So when we have infinities in intercepts, so the first thing that we need to do in that case is that we first draw those intercepts which are not infinity, and we deal with infinities at the end. Okay, we deal with the infinities at the end. First we need to draw these two intercepts. This is a2 intercept, and intercept means the point where the plane touches the a2 intercept. A2 intercept means the point where the plane touches the a2 axis. This is the a2 axis. This whole line is a2 axis, and these axis lines are actually really important when it comes to planes. In case of directions, we have coordinates. We get coordinates from Miller indices in case of directions. And coordinates means starting from origin, you'll move that one along A1 direction, then that one along A2 direction, and that along Z. It's like you are on a ride and you continue to move ahead. But in case of planes, you always start from origin separately for each axis line. Okay, so let's do that and it will be clear to you people. So A2 intercept is positive 1. A2 intercept is positive 1. It means starting from origin, we'll move along positive A2 direction. So what does 1 means? 1 means from one corner to the other corner of the unit cell along axis direction. Okay, all the lengths which are from one corner to the other corner of the unit cell which is parallel to at least one axis direction, then that length will be taken as 1. Okay, and for example, here let me draw it first, then I will elaborate that point. So this is origin. Origin is also taken as corner point. Keep that in mind. Though you can see, you will assume that this is not a corner point, but it is a corner point. Origin is always one of the corner point. It is treated as corner point. So this is the corner point starting from origin to the other corner of the unit cell along A2 direction. So this is here. This is A2 direction. To the other corner is this corner. So we'll stop here, and this point is one of the point on the plane. I'll shade it in green. I hope you can see the green color. This is one of the point on the plane. Okay, and only that point. This point is called as intercept because the plane touches that A2 axis line at this point. Okay, and next we have the A3 intercept, which is -1. A3 intercept is -1. So this is positive A3 direction and this is the negative A3 direction. Okay, intercept is -1, which means starting from origin, again starting from origin, not from this point onwards, but starting from origin again, we'll move one unit along negative A3 direction. So this is positive and this is negative from one corner to the other corner of the unit cell. And this is the point, another point on the plane. All right, now the next step is to deal with infinities. We have got 2 points on the plane. Now the next step is to deal with the infinities, and we can see that the z-intercept is infinity and the a1 intercept is infinity. So let me tell you the rule, which is that whenever they are infinity, the points that you have already got, for example, we have got 2 points here, you'll draw parallel lines from these points along the direction which is having infinity as intercept. Okay, let me do it. It will be clear to you people. So we can see that the a1 intercept is infinity. Okay, what is a1 direction? This is a1 direction. All these directions, this, all these are a1 directions. So from this point, not along axis lines now. Okay, infinities are treated differently. So from this point, which we have already calculated and determined on the plan, we'll draw parallel line to a1 direction. This is a1 direction. We'll draw parallel lines and we'll stop to the other corner of the unit cell. We have reached the other corner, so we'll stop. Okay, we have stopped. Now from this point we have drawn the parallel line along a1 direction, but we can't do for this point because if we do so, we'll move outside of the unit cell, which is not allowed. So we'll not draw a parallel line from this point for this particular direction. That is it. Now the next is the intercept, which is infinity. So these are the 2 points that we have determined. We'll draw parallel line to the z direction. So the z direction is vertically upward. So from this point onwards, infinities are treated here. So we'll draw parallel lines along z direction, which is this point, which is this motion, sorry, and we'll stop to the other corner of the unit cell, which is this point. We'll stop where the other corner of the unit cell is reached, and we will continue to move until the corner is reached and we are not going outside of the unit cell. Okay, we have to remain inside the unit cell. That is the rule. So from this point onwards, we'll also move along the z direction, parallel to z direction from all the points, okay, that are available. These were the 2 points. So we'll do the same here. parallel to z direction, which is vertically upward, and we'll stop when the corner is reached. Here the corner is reached. And now these are the 2 points, we'll join them together. And we have got the plane, which is this. Okay, it's like that. Like that. Like that, and vertically upward. This is the plane. The first plane, which is 0, 1, 1 bar, 0. I hope you got it. Now let's do the next one, which is really interesting and really has a different shape. Here is the next one. We can see this is the H index, K index, I index, and L index. Let's form the table now. We'll find out the intercepts. This is H, K, I, and L. These are indices. You'll write in sidebar. We'll write the indices here. H is 1, K is -1, bar means it's negative, I is 0, L is 1. Next, we'll take in reciprocal. Taking reciprocals. Taking reciprocals is all it takes to find out the intercepts, okay? And we will use those intercepts to draw the plane inside the unit cell. The only tricky thing here is to deal with the intercepts and how to find out those points. Okay, you should practice it many a times in order to, be confident about it. So taking reciprocal, we'll divide by 1. 1 divided by 1, which is equals to 1. 1 divided by -1, 1 divided by 0, 1 divided by 1. 1 divided by -1 is -1, 1 divided by 0 is infinity, 1 by 1 is 1. So we have got the intercepts. This is 1, -1, infinity, and 1. Hence, this is the A1 intercept. This is A2 intercept. This is A3. And this is Z intercept. Let's draw the HCP unit cell and then we'll draw the plane. We'll follow the similar steps to draw it again. This line, this is forward line, and then 3 lines difference and a backward line, slightly backward. Again, we'll have that forward line right below this one and this backward line right below, and 3 lines difference again. Join them together at the center point. This is center point. This is center point. Join them together like that. Okay, now next, join the equivalent points together. These 2 points are equivalent. This upper point is equivalent to this point, so joining it. Then this point is equivalent to this point, so joining them. This lower point is equivalent to this lower point, joining them. This point is equivalent to this point, joining them. It sounds like a song. This upper point is equivalent to this point, joining them. Yeah, we have got the HCP unit cell, and this is the origin. This is positive A1 direction, leaving this corner. A2 direction, leaving this corner. A3 direction. Negative A2 direction, positive A2, negative A2. Positive A1, negative A1. Negative A3. Z. Okay, and we have this corner point. As we can see that this is the roof point. It starts from origin at the center point. This line will end at center point of the roof. Okay, which means this is one corner of the unit cell and this is another corner of the unit cell. It will help here in this case, that is why I'm mentioning it. So let's do that. We have following intercepts, as we can see. A1 intercept, A2 infinities will be dealt at the end. So let's start with A1 intercept, which is positive 1. So positive 1 starting from origin in positive A1 direction to the other corner of the unit cell. So starting from origin, this is A1 direction positive. So from one point to the other corner of the unit cell, which is this point, this is positive 1, and this point, this one point, is point on the plane. Okay, this is point on the plane. This has nothing to do with the plane. This single point is only a point on the plane. That is what intercept means. Next we have A2 intercept, which is negative 1. So starting from origin again, all over again, we'll always start from origin for each of these intercepts. Okay, so starting from origin, negative 1, it means in negative A2 direction. This is negative A2 direction from one corner to the other corner of the unit cell, which is this point. So this point is negative A1. This is another point on the plane, this point and this point. Now next infinity will be dealt at the end. Next we have z-intercept, which is 1. Starting from origin all over again, and 1 means one corner to the other corner. So this is one corner. Origin, starting from origin, will move vertically upward, which is z direction. So we'll move vertically upward and we'll stop when the corner is reached, and the corner is at the centermost point. So this point is a point on the plane, this point. This is positive 1. Okay, this is a point on the plane, this is a point on the plane, and this is a point on the plane. We have got 3 points on the plane, and we have A3 intercept as infinity. So we'll draw parallel lines from each of these points parallel to A3 direction. Okay, which could be negative or positive, because infinity has no polarity sign in here. Okay, it's not positive infinity or negative infinity, it's simply infinity. Okay, so it doesn't matter whether you are drawing parallel lines along negative A3 direction or positive A3 direction. That doesn't matter. It should be a A3 direction at least. That's what is needed. So we'll draw parallel line. Let's consider this point. Okay, and I'm gonna draw a parallel line from this point along the A3 direction, and A3 direction is this horizontal direction. Okay, all these horizontal motions are along A3 direction. So from this point we'll draw parallel line along A3 direction, and we'll stop at the other corner of the unit cell such that we do not move outside of the single unit cell. So we can't move further on, because otherwise we'll move outside of the unit cell. So we'll stop here, and from this point we can't draw any line parallel to A3 direction because it will move outside of the unit cell, so we don't need to. Okay, just it's fine. Now from this point, a really interesting point, you can see it's the center point, and this horizontal line will be the parallel to A3 direction. So starting from this point, I'll draw a parallel line along A3 direction. This is A3 direction, negative A3 direction. So we'll stop at the other corner of the unit cell. But it can also happen in this direction because it's valid. We can move it because we have not reached another unit cell. It's inside a single unit cell. So from this point we'll draw also a parallel line, and we'll stop to the other corner of the unit cell, which is this point. We can't move any further now. This is the end point and this is the end point. Okay, we'll draw a parallel line in both directions, keeping in mind this limitation that it shouldn't move outside of the single unit cell. Okay, so this was the center point. We can draw it here, like here, and not further than that. We moved it here, but we can't move it here because it will move it to the next unit cell, and that is not allowed. Okay, everything should happen inside a single unit cell. That was the rule. Now this is the point, this is the point. Join them together. Join these 2 points together and these 2 points together. This is the plane. Okay, it's like that. Okay, like that, from center to like that. Okay, I hope you can imagine it, and you don't need to imagine it because you have drawn it, okay, the correct way. So I hope you are clear with the steps that find the intercepts points on the lattice first. Okay, we found this point, and this point. All right, and we had another intercept here which was infinity. So from each of these points we have to draw parallel lines along this infinity direction. Okay, and we drawn the parallel lines, and then we joined all these points, final points, together to form a closed figure. So we join this, and we get the final figure. Okay, final figures are always obtained by joining the intercepts together. Okay, don't confuse it with these motions, they are not the part of intercepts. As I told you people earlier, these points matters, okay, that we get at the end. So we'll join them together and we get the final figure. This is the third plane that we have, and this is the H index, this is K index, this is I index, and this is the L index. As we can see, there is a single bar over these two numbers. It means that both of them are negative. Okay, so whenever they are consecutive negative numbers, negative indices, you can, instead of this, you can also do this. Both of them are correct. Okay, so let's draw the table, the fancy table. This is H, K, I, and L, and we'll write that they are indices. The first index is 2, second is -1, third is -1, and L is 0. Now we'll take the reciprocal, taking reciprocal 1 divided by 2, 1 divided by -1, 1 divided by -1, 1 divided by 0. 1 by 2 is again 1 by 2. 1 by -1 is -1. 1 by -1 is -1. 1 by 0 is infinity. So these are actually the intercepts that we get after taking the reciprocal of these indices. And we have, this is A1 intercept, this is A2 intercept, this is A3 intercept, and this is Z intercept. All right, so now let's draw the HCP unit cell, and then we'll draw it, and I'll speed it up so that you may not have to watch it again. We'll join them together like that. Joining the equivalent points together. This center point is origin, positive A1 direction, leaving this corner, positive A2 direction, leaving this corner, positive A3 direction, and vertically upward is the Z direction. All right, and we know the negative directions as well, and we should just mention them so that it's easy for us to navigate. It's negative A2, negative A1, and this is negative A3. That is what is required. Now we have A1 intercept as half. What does half mean? So what does 1 mean? First of all, let's see. It's from one corner to the other corner of the unit cell along the axis direction. This length is taken as 1. Keeping in mind that it's from one corner of the unit cell to the other corner of the unit cell, and it's parallel to at least one axis direction. So that in that case, this length will be taken as 1. Half of it means halfways. Okay, so that is how we calibrate all of the lengths. When it's 1 by 3, it means that if this length is 1, 1 by 3 means divide it into 3 equal parts. So 3 equal parts, 1 part, 2 part, 3 part. Okay, so each part is 1 by 3. And 1 by 4 means dividing the line into 4 equal parts. This is 1 part, second part, third part, and fourth part. Okay, that is how we do the partitions based on the intercept we have. The A1 intercept is half. We can see 1 by 2. So what is the positive A1 direction? Starting from origin, this is positive A1 direction. So what constitutes 1? From this corner to the other corner of the unit cell, this is 1. This length is 1, but we need half. Half is the point where the intercept is. So dividing it into half, which is roughly this point, you can see I first calibrated what is 1, and then we divided it into half. Always do that. Okay, don't just roughly put this line anywhere. First decide what 1 is, then divide it into half. This is the point on the plane. All right, next is the A2 intercept, which is -1. A2 intercept is -1, really simple. This is positive A2 direction, negative A2 direction, -1. So starting from origin again to the other corner of the unit cell, which is this corner, -1. This is another point on the plane. Okay, next is negative A3 direction, which is which is negative, next is A3 intercept, which is -1. So positive A3 direction, and this is negative A3 direction. Starting from origin again, we'll move 1 unit along the negative direction, which is this point, to the other corner of the unit cell. This is -1. This is actually a really tricky diagram. Now, since the z-intercept is infinity, so we got 3 different points, and we'll draw parallel lines from each of these points along the z direction, okay, such that we are inside a single unit cell. Since infinities are dealt, we'll draw the continuous line, which will be the part of the plane. So from this point, we'll draw a parallel line along z direction, and we will start moving from this point, and we'll continue moving until the end is reached. So this is the point to stop. Next, from this point onwards, we'll move upward, vertically upward. We'll draw a vertically upward straight line such that the similar point over here somewhere at the middle is reached. Okay, similar to this. Okay, where this is located, since this thing is similar to this thing, so where this point is, you will stop where this equivalent point is. Okay, next, from this point onwards, we will draw straight lines parallel to z direction, which is this, and we'll stop to the other corner of the unit cell, which is this point. Okay, now we'll join these points together. So this and this is the straight line. Okay, and similarly here, this will be the straight line. Okay, this is straight line, they all cut each other, and this is actually the plane. I hope you can see it. Okay, this was really tricky, as you hardly imagine that these 3 points will just seamlessly cut each other. And here at this point, I want to mention one of the most important point while drawing the planes in hexagonal crystal system, and it is that H, K, and I indices are actually connected with each other through this equation. And this relation between H, K, and I, which are actually representing the intercepts for A1, A2, and A3, hence we can talk about the intercepts as well. So the intercepts A1, A2, and A3 will lie in the same line. Okay, this is the result of this relationship between H, K, and I. They are linearly dependent upon each other. Okay, that is why they lie on the same straight line, and that will always hold. So let's see the main consequences this relation brings, and it brings a kind of easiness in drawing the planes. Now let me tell you what it is. The easiness is that whenever the A3 intercept is not infinity, okay, when A3 intercept is not infinity but some other number, then you can skip it or you can ignore A3. It is not needed to draw the plane, because we know that A1 and A2 and A3 always link together to form a straight line, so we don't need exactly A3 to draw the plane. All right, you will see this thing in the next figure, because incorporating or including A3 complicates the figure, because sometimes since the figure is not accurate, we can't see them making a straight line, but they form a straight line when you are drawing it accurately. That is why it's a kind of easiness that we can enjoy, and it happens whenever the A3 intercept is not infinity. However, for the cases where the A3 intercept is infinity, as we saw in the first two examples, the A3 intercept was infinity, it is crucial and important to incorporate A3 while drawing the plane. Okay, that's important. But for those cases where A3 intercept is not infinity, it's some other number, as we saw in third example, we don't need A3. You'll draw this figure even not including the A3 intercept, and we'll see in the next problem that including the A3 intercept creates a problem. So you can skip A3 intercept. You'll see it later in this problem, the next problem that I'm gonna do. So for that purpose, keep that noticed down. Now note it down for drawing the planes in HCP, and it's the most important point to consider. And it is that whenever the A3 index, we are talking about indices here, whenever the index is 0, whenever the A3 index is 0, you have to include it in the process. When it's not 0, you don't need to include it. Alright, so that is the most important step. So let's continue with the next problem. And this is the next pen in line, and we have one double bar, which bar, which shows there is a single bar above both of these numbers. It means both of them are negative. Okay, H index, K index, I index, and L index. Let's draw the figure. H, K, I, and L. These are indices. It's -1, -1, 2, and 2. Taking reciprocal. 1 divided by -1, 1 divided by -1, 1 divided by 2, 1 divided by 2. It's -1, 1 by -1 is -1, 1 by 2 is 1 by 2, 1 by 2 is 1 by 2. These are the final intercepts for the plane. This is A1 intercept, A2 intercept, A3 intercept, and Z intercept. Now let's draw them inside hexagon and unit cell. I'll speed up the drawing. I have it here, and this problem is very important. Okay? This and the line slightly backward. I'll try to make it as accurate as possible so that we can get a really close enough line. Join them together. Now join the point together. This point is equivalent to this point. Opposite like that. This point is equivalent to this point. This lower point is equivalent to this lower point. This lower point is equivalent to this lower point. And this other point is equivalent to this other point. This point is equivalent to this point. This is the region. A1 direction, A2 direction, A3 direction, Z direction. Okay, and if it starts from center, it will end at center. That's the rule in HCP. Okay, so and we know the negative directions as well. This is negative A2 direction. This is positive A1. This is negative A1 direction. As you can see, we have negative intercepts as well. So we would need that. This is negative A2 direction, but it is not needed, so I'm not gonna draw it. A1 intercept is -1, -1. So -1 means starting from origin, we'll move to the other corner of the unit cell along negative A1 direction, which is this. So this is the other corner along negative direction. So this is one of the point on the plane. This is one of the point on the plane. Okay, next we have -1 as A2 intercept. Starting from origin, what is negative A2 direction? This is negative A2 direction. Starting from origin to the other corner of the unit cell along negative A2 direction. This is the other point on the plane. As you can see, it's -1, -1. Okay, next is the A3 intercept, and A3 intercept is half in positive. So this is starting from origin to the other corner of the unit cell. This whole length is 1, and half of it is somewhere here. But as I told you people earlier, you should know that these three intercepts of A1, A2, and A3 should form a straight line. Okay, and it's not forming a straight line because my figure is not perfect. Okay, that is why you are supposed to do this. Okay, That is a really big hint that I am giving you, people, because when it's infinity, that problem doesn't arises. All right, the figure that you obtain is really close enough, but when it's not infinity, it creates problem. So since a1 and a2, they all link together through a straight line, you don't need a3 when it's not infinity. When it's infinity, you have to keep it in the process. All right, keep that in mind, otherwise you'll get confused. So what I'm saying is that you only need a1 intercept, a2 intercept, and z intercept to draw the figure. All right, you don't need a3 intercept until unless it's infinity. If it's infinity, you'll need that, as you saw in the first two examples. All right, so we'll use a1, a2, and z, and we don't need a3 as here. And I showed it here because you need to learn that. You need to learn that why I didn't incorporate a3 in here, because of the inaccuracies in the figure. You may get disoriented, you may get somewhere else, your shape can be disturbed. So a1 and a2 will ensure that you are getting the right figure. So join the point a1 to a2, that is what is needed. And yeah, this is one of the line on the plane. Next, we have the z-intercept as half. Starting from origin, you will move to the other corner of the unit cell, and this is the other corner. This whole length is 1. Take half of it, which is this point. This point is half. Now, okay, this is a half point, so this is another point on the plane. Now join these points together to form the closed figure. So this and this. This is the plane. Okay, you can shade it like that. So you have got the plane, which is double 1 bar 2 2. This is it. Now let's do the next one. Here we are with the Miller indices. Now we have these Miller indices. This is H, this is K, and this is L. But we don't know about I. There is a really interesting fact and relation between Miller indices and Miller-Bravais indices. As I told you people earlier, Miller-Bravais indices are 4, H, K, I, and L. And Miller indices are 3. Okay, it's a really interesting fact that they are the same, but I is only an additional thing. You can see that H of Miller-Bravais indices is similar to the H of Miller indices. K of Miller-Bravais indices is similar to K of Miller indices, and L, the last one, is similar to this L. But I is only different, and I is obtained from H and K, like that. The equation that I told you people earlier, this one, so that equals to 0, and I would be equals to negative of H plus K. That is really simple. So there is a really interesting relationship between Miller indices and Miller-Bravais indices, while in case of directions, they are not equal, they are all different. Okay, in case of direction, the case is really different, but in case of plane, the case is really simple and straightforward. That H, this is, so we need to only find out I, and I is obtained by negative of H plus K. H is 0 and K is 1, so 0 plus 1, which gives minus 1. Hence we have H 0, this is H, this is K, 1, I that we calculated, L is same that was in Miller indices. The only difference is I, and I could be calculated from H and K. And as we see in this case, that if I is not 0, okay, if the intercept corresponding to I is not infinity, they are the similar statements, because if the index is 0, then the intercept is obtained by taking the reciprocal of index, and 1 over 0 is infinity. So it's a similar statement that if I is 0, then you have to consider it, But if I is not 0, if I is something else, then you don't need to consider it while drawing the plane, because that doesn't matter. Okay, so all that will matter is h, k and l for us, but we have to confirm that whether I is 0 or not, whether the intercept corresponding to a3 is infinity or not. They are similar statement. Okay, just I'm making sure that you are understanding it completely. So it's h, k and l that matters, but you need to find out I to see whether it's 0 or not. If it's 0, you have to incorporate that infinity nature and you'll draw accordingly as we saw in the first two examples. But if it's not infinity, then you can ignore it. You don't need that to draw the plane. So let's consider h, k and l further on. Let's do that. H, K and L is all that matters. So it's 0, 1 and 1 here. These are indices. And it's only true for planes, not for directions in HCP. These are indices taking reciprocal. Reciprocal 1 over 0 is infinity, 1 over 1 is 1, and 1 over 1 is again 1. So we get infinity, 1 and 1. This is A1 intercept, A2 intercept, and Z intercept. Keep that in mind. Let's draw the HCP universal. Since all of them are positive, so we don't need the negative directions. And this is the origin. We'll deal with the infinity at the end. And we have A2 intercept, which is equals to 1. So starting from origin, we'll move in the positive A2 direction to the other corner of the unit cell, which is this point. So this is one of the point on the plane. Next is the Z intercept, and it is equals to 1. So starting from origin again, we'll move vertically upward to the other corner of the unit cell along positive z direction. So if we start from center, it will end at center. So this is the point 1. This is another point on the plane. This is first point and the second point, and we have A1 intercept to be infinity. So as we saw earlier, we'll draw a parallel line from these 2 points along the A1 direction. Okay, and we'll stop at the point where the unit cell ends. So this is A1 direction, this is A1 direction, all these directions, these, okay, these directions, all these directions are A1 direction. So from this point, we'll draw a parallel line along A1 direction, which is this direction. I have not drawn it perfectly, but these lines are parallel to each other. So this is the parallel line, and we will end at this point to the other corner of the unit cell. Okay, we will not proceed it further. As you can see, this is the continuous line, and the line that you draw and travel when you are drawing the infinities, when you are dealing with infinities, are the part of the plane. Okay, this line is part of the plane. Now we have this point, so from this point we'll draw parallel line along A1 direction. So we'll draw it like that from to the other corner of the unit cell. Okay, but as we saw earlier, this line is also parallel to A1 direction, okay, which is in negative A1 direction, but it's also included because it's within a single unit cell. So we'll draw this line. Figure will be obtained by joining this point with this and this point with this. Okay, and hopefully, but it's really tough figure to imagine. They are joined together, and then these endpoints, singular points, are joined together. So this is the plane. Obviously, if you draw the HCP unit cell accurate enough, you will get the most promising figure, but that's all we can do in here. So that's true. If you have used the method correctly, any figure that you are going to draw will be correct. This is quite a accurate figure. Let me try it here. So this was the point, and this was the point on the plane. parallel line along A1 direction, this, and like that. I joined this together and these two together. Kind of similar, but we can see the shape, the four-sided shape now, at least like that. Okay, so that is it. Now let's do the last one, which is 1 bar and 1. Okay, so this is H, K and L. We need to calculate I to see whether it's 0 or not. So here H is 1, K is -1, 1 minus 1 is 0, so I is 0 here, and hence since I is 0, then it has to be incorporated into the process. Since I is 0, hence we need it. If I would have been any other number other than 0, we wouldn't need it in the process, but since it's 0, we need it. So it will be in the process, and we'll be considering I as well. So let's draw the table here. H, K, I and L. We have H1, K -1, I is 0 and L is 1. Taking reciprocal, 1 over 1 is 1, 1 over -1 is -1, 1 over 0 is infinity, and 1 over 1 is 1. So we get 1, -1, infinity and 1. Let's draw this plane now, and for that purpose I'm going to now you're pro in drawing the HCP. So the first intercept, A1 intercept is 1. So starting from origin to the other corner of the unit cell along the A1 direction, this is the point on the plane. Next is -1. So this is positive A2 direction and this is negative. So starting from origin to the other corner of the unit cell along negative A2 direction, this is the other point on the plane. Alright, next we have the z-intercept, which is equals to 1. So starting from origin, we'll move 1 unit along the z direction. We'll stop to the center point because this is the end point, starting from center, ending at the center. So this is the next point on the plane. Next we have A3 intercept, which is infinity. And if you remember, this is similar to this case. Okay, if you represent this case in Miller-Bravais indices, this is the representation, as we get I0 here as well. So we'll draw parallel lines from each of these 3 points along A3 directions. From this point, we'll draw a parallel line along A3 direction, which is horizontal. So we'll stop to the other corner of the unit cell here. From this point, we'll draw a parallel line along A3 direction, which is this to the other corner and this to the other corner. We'll join these endpoints, not center points. This center points are not considered, only endpoints are considered. So we'll join them together like that, and we got the plane. So that is it for this video. I hope you got it, and you must remember these hacks. Whenever I, which is index, is 0, you have to consider it in the process. Whenever I is not equals to 0, you can ignore it and play with HKL only. Okay, so that is the crux of this video, and I told you people about infinity, dealing with infinity. While drawing the intercepts, you only take those points. Okay, but while dealing with infinity, the lines that you get through are actually the part of the plane. Okay, these continuous lines are the part of the plane. So have that difference in your mind, practice it many a times, and I'll meet you in next video.